Hey everyone. So sorry about getting this one up a little bit late. I have some college students prepping for finals, so I've been trying to squeeze in getting these done while I have a chance. As usual, so this is the set 2 from the first administration for AP Physics C Mechanics. As usual, if there are any corrections, I'll put them in the description below, as well as I will have a link to the actual handwritten solutions that'll look a little different than the ones I put up here, but basically the same. And at the end, I'll give you my thoughts about like how they compared. Okay, so student designs experiment using block of adjustable mass to investigate friction using the setup below. Block 1 of initial mass 0.44 kilograms placed on a rough horizontal surface connected by a string to block 2 of minimal mass. The string extends over a pulley that has negligible mass and friction. Calculate the minimum value of the coefficient of static friction that would keep the two-block system at rest. Okay, so free body diagrams. Block 1 has got gravity down here and then normal force up here. Also got frictional force holding it in place. Static friction specifically, and then we have tension here, and then we have a tension here on this guy, and 0.2 G coming down on this guy. Okay, so those are all the forces, nothing else is touching. Calculate the minimum static friction that would keep the two-block system at rest. So basically everything's in rest, so the net force is a 0, so that means specifically the normal force up here is equal to 0.44 G. We also have the frictional force, static friction is equal to tension. We also have from this free body diagram, tension equals 0.2 G. So putting that together tells us that the force of static friction has to be 0.2 G. Now, static friction has to be smaller than mu static times the normal force, and that's mu s times 0.44 G, right? So the minimum that coefficient, so let's see, yeah, so that means if you solve for mu s has to be greater than or equal to 0.2 G over 0.44 G, which is equal to just 0.2 divided by 0.44, 0.45, 455, I guess, if you want to be rounding. So mu has to be bigger than this quantity, and so this is the minimum value. The coefficient of friction is such that when block 2 is released from rest, block 1 travels across the surface. Acceleration A of each block is recorded, and they're recorded to be about the same. Just, the data is always detected, which makes sense. Like, the two objects have to move with the same acceleration. On the dots below represent the blocks. Draw and label the forces that act on each block. Each force must be represented by a distinct arrow. Okay, so we already did this. Here we have force of gravity on block 1. We have the normal force on block 1. We have a tension going to the right. And then we have kinetic friction now, because now that they're sliding. We have here tension pulling up, and then force of gravity on 2 on the bottom. Now, so that's it. Calculate the coefficient of kinetic friction between block 1 and the table. So now everything is accelerating downwards. So you have to think of, or block 2 is accelerating down, block 1 is accelerating to the right. So when you do our net force equations, here we're going to say T minus the force of friction of K is equal to mass 1 times the acceleration. And that's because this guy's accelerating to the right. In his vertical direction, you know that Fg1 has to equal the normal force. And that's because in the vertical direction, it's not accelerating, so net force is 0. Here you would say Fg2 minus T is equal to M2A. So let's kind of like, so we've done our net force equals MA. Now we kind of need to do a little bit of substitution. Here T minus mu K Fn1, because the force of friction, kinetic friction, is always equal to mu times the normal force, as opposed to static friction where it's like less than or equal to. And here you have M2G minus T is equal to M2A. So we can plug in T, or more simply, we just add these two equations together. So when you put those two together, the T's and the T's add to 0, so you get M2G minus mu K Fn1 is equal to m1 plus m2 times a. And so then you can rearrange m2g minus m1 plus m2a is equal to mu k fn1, which is mu k m1g. And so mu k is equal to all of this divided by all of this. So m1 is equal to 0.2 kilograms. m2 was the 0.44 kilograms. And the acceleration is given by the graph. We're going to estimate it. Let's see, it's 2. Each hash mark look like 0.2. 1, 2, 3. No, 0.25. So why don't we say 2.25? 1, 2, 3, 4. No. 1, 2, 3, 4. Yeah, it's 0.25 each. So we just plug that into a calculator. 0.44. 0.64. Divided by 0.2. I got. Ooh. I did not get the right answer. Let's see. M1A. Oh, did I mix these up? Oh, yeah. M2. I mixed up in my head. Let me just double check the numbers. The mass of block 2 is 0.2, and the mass of block 1 is 0.44. Whoops. That looks more right. M1 is 0.44 divided by 9.8. Yeah, I get 0.12. Okay. All right. Careful measurements determine the coefficient of friction is larger than the calculated value in part C. Does the following explanation sufficiently account for the observed discrepancy? The horizontal table was not perfectly level before the experiment was conducted. The observed difference in the angle accounts for the difference in the expected and calculated values of mu k. So does that make a difference? Well, let's take a look at how we've got the mu k. If I look at my calculations here, mu k was equal to the m2g minus m1 plus m2a over m1g. So what is changing the angle? Well, so first things you have to think about, what is the angle change going to do in the original problem? If I tilt this, like this, what it's going to do is it's going to change the acceleration for sure. But it's also going to change the normal force. So I kind of want to think about so if we kind of tilted this, let's see, the tension. So the normal force changes. You have a little more gravity pulling on you down here. And you have a little bit less friction because the normal force is now a little bit weaker. So you have less friction, you have more gravity, so you can have more acceleration on this guy. More acceleration on this guy means the tension is slightly less, but basically the acceleration goes up and the normal force goes down. So where does the normal force kind of come into play? Like which of our equations would sort of change when we did this? It would have to do with the normal force. So where's the part we do the normal force? Is this one? So let's look at this equation here. This is probably the more useful equation because here we know that m2 and g are constant, m1 and m2 are constant. We know that a is going to go. So instead of m1g down here, I'm going to make this the normal force because that's really where it comes from. And so we say the acceleration is going to go up and the normal force is going to slightly go down. Overall, that's a weird balance, but it's not going to go. I think it's hard to say, but it definitely could change it. So it's not going to be like a linear relationship because how does the normal force go down? The normal force now becomes m1g cosine theta. but the acceleration is going to get an added part. It's going to be a very complicated dynamic, but it's going to go up by like g sine theta a little bit. So I think there's a non-linear relationship between acceleration and the normal force. I think this is a little bit hard to explain. So I would say yes, because even though the acceleration going up will reduce the numerator and the normal force will go down, they won't go down by the same amount, basically. And it would be kind of a little bit complicated of analysis to fully derive. But I guess my answer would be, well, the acceleration increases, at least to say that. The normal force slightly decreases. That's going to slightly decrease the, which causes then friction slightly decreases. But that's related to the acceleration, so I guess that's not really that important. So I think what that tells us is, but they change in separate ways. Actually, one way to think of it is for very small angles. Here, we'll use a small angle approximation if you want to kind of think of it that way. I didn't think about this before, but you could think of this as for small angles, this is g delta theta. And for small angles, this is really m1g. Like, the normal force doesn't change very much. And that's because the cosine curve, if you look at the graph of cosine, or from an approximation point of view, cosine is roughly constant here, but a sine curve kind of like goes up like this. So there's like a lot more dependency on the angle. All right. So I actually would say that the acceleration increase normal slope very slightly decreases, which results in mostly that the mu decreases or the mu changes. Now, they didn't say which way that the table was angled. So even though in this picture, when I said the acceleration was going up, that would mean mu k was going down. Okay? What you can say is that, well, if it was tilted the other way, then the opposite thing would happen. The acceleration would decrease, and thus the mu k would, the theoretical mu k, or the measured mu k would then go up. Okay? So, because they didn't say which way the table was kind of sloped, it's still possible. So you could acceleration, let's say, decreases, if you want to say it that way, and mu k increases. Because from this relationship, the acceleration would go down. And the normal force would be about the same. Like I said, cosine has a very weak dependency on the small changes in angle, whereas sine has a larger dependency on small changes in angle. So, okay, cool. I think that part was a little bit harder than the set 1 question. All right, cool. Let's look at this one. Experiment is moved to a surface with negligible friction. Run for trials. Each trial, the student varies the mass m1, m2. While keeping the total mass constant. The data for the acceleration are shown on the graph. Draw best fit line for the data. I'm going to make it go like, like that. Okay. And then we're going to say, okay, so using straight line, calculate experimental value for the gravity g. So now I don't have friction to worry about, that weird dynamic. So really, if you look at the system, if you look at the two blocks as a system, I really just have m2g pulling down, and then no friction, and then the total mass is m1 plus m2. So I would say I have net force equals m2g, and that's equal to m1 plus m2 times a. And so the acceleration, which is the y value in this case, would be m2g over m1 plus m2. But we know m1 plus m2 is constant, so this is simply g over 0.64 m2. Okay, so that's our relationship. That means if this is my y value and this is my x value, my horizontal axis, then this has to be my slope. So that means we calculate the slope here. So let's pick a value here. Let's pick like, I don't know, let's say there. I always pick 2 points that are far apart. Okay, so this is 0.1, 0.3, and this point here is 0.45, because this is 0.5 here. So this is 0.45, this is 0.05 for the x-axis. And the y-axis, this is like 1, 2, 3. Yeah, each one is 1, so this is probably about 0.5. And then this guy is about, I don't know, this is 7. No, each hash mark is 1, and so this is like, I don't know, 6.3. Okay, so then we would say the slope is equal to 6.3 minus 0.5 divided by 0.45 minus 0.05. And that's equal to g over 0.64. So you can solve for g. You just take this value and then multiply by 0.064. At 9.28 meters per second squared. Obviously, your answer will vary depending on how you drew your line. So don't be too like, but it should be something reasonably close to 9.8, plus or minus like 1 or 2 meters per second squared. Students lift the end of the surface, so the surface incline is angled. They lift the left end, so they're going to make it tilt down a little bit. And run the experiment for M2 equals 0.2 kilograms is repeated. Would the acceleration system be greater than or less than or equal to the acceleration in the original experiment? Greater than, because for what we talked about is that the net, there's going to be, if you think about it from your system and you have it like this, you now have an additional force. So you would say for the total system, we have an additional component of gravity, mg, and then the component in the direction would be mg sine theta, right? Additional force. Which block is it? I get confused on which block it is. It's M1 is on the left there. M1 g sine theta contributing to the net force, contributing in the direction of acceleration. So we have a larger net force, total mass is the same, and that results in larger acceleration. Okay. Number 2. An object A is a long, thin, uniform rod of mass m and length 2L that is free to rotate about the pivot of negligible mass at the left and shown above. Using integral calculus, derive an expression to show the rotational inertia. IA of the object about the pivot is given by 4/3 ml squared. Okay, so you have a little bit of a slight dx here, and it's how you want to set up. But like it's uniform density. So what is the density equal to? It's equal to the mass over the entire length. So when you set up the I calculations, you want to do the integral of x squared dm. That's the integral of x squared lambda dx. So lambda is a constant I can just bring outside of the integral. And here I'm going to integrate from 0 to 2L. Don't forget you're going for 2L. So they're trying to trick you a little bit there. This is going to be 1/3 x cubed from 0 to 2L. And then I just plug in 2L. Because when I plug in 0, I get 0. So I plug in 2L. So this is going to be m over 6L times 2L cubed, which is 8L cubed. Because just to spell that out a little more, you're doing 2L quantity cubed. So that's 8. 8 over 6 is 4/3. Or it's 4. And then, yeah, 8 over 6 is 4/3. L cubed and L become L squared. So that's it. Okay, object B of total mass m is formed by attaching 2 thin, uniform, identical rods of length L at a right angle. Object B is held in place as shown above. Express your answer. Determine the following of the given coordinate system shown in the figure. The x-coordinate of the center mass of object B. Okay, so here we one thing you want to do is, we know, because it's uniform density, we know that this rod has a center of mass right here, and this rod has a center of mass right here. So for the center of mass, we don't have to do an integral calculation. You do have a linear weighted sum, because if you're going to do discrete masses at different points of center of mass, then you can simply just do the weighted sum of the mass. So we could say, well, this guy has a mass m. Well, it's mi(xi) over the m total. This is the general form. So we're going to add up. So this guy, he's located at L over 2, and he has a mass of big M. Then this rod here is located, x coordinate is L. You see, with the x, I only care about the x coordinate. I don't care about the vertical position. That will matter for the y coordinate of the center mass. He's located at x equals L over here. All the mass is distributed here. And he has a mass m, and the total mass is 2m. So this is 1 plus 1/2 is 3 halves Lm divided by 2m, and that's going to be 3/4 L. The y coordinate of the center mass is going to be the exact same, because he's located at a height of L over 2, and he's located at a height of L. So you can do the exact same calculation. He's also at 3/4 L. So that means the center of mass is somewhere located around here. It's okay that it's not on the object. That might feel a little weird, but it is okay for the center of mass to be not as physically attached to the object. Okay, object B is a rotational inertia IB. Is the value of IB greater than or equal to IA? Well, you added another mass at the end here. And so, like, this is object A, so you added a mass at the end. It was going to increase I. Greater than. Has a larger, so it's the same shape, has the same rod as A. Wait, actually, let's see, it's only L. Because the original one, was 2L. Oh, that's a little different. I thought it was just... okay, so we've bent it. So the original one looked like this, and we've bent it down. So we took all of this mass that was here and put it only this far away from the pivot. So we actually were going to reduce the I, because we're going to take all the mass that was here, because remember the original IA was 2L, but then we're going to chunk that off and then put it here instead. And so then that's going to reduce I. When I first read it, I thought it was we did it, but you're right. It starts 2L, and then you chunk off a piece. So we have the second half of rod A is further than the vertical segment further from the pivot than the vertical segment of rod B. So the mass is not as distributed. It's distributed closer, which means closer to the pivot, which means smaller I. Okay. So object B is released from rest and begins to rotate about its pivot. On the axis below, sketch the graphs of the magnitude of the angular acceleration and angular speed of the object as a function of time. It is released to the time the center mass reaches. Okay, so the torque, the net torque is equal to IB alpha. So alpha is equal to the net torque over IB. What's the net torque on the system? Well, if you kind of like draw this guy, and let's say he's rotated a little bit, like let's say at an angle, because we want to see like how the torque is going to change. This is very similar to the set 1 problem. It's just the shape is a lot weirder. Okay, so this guy's, if you think about all the forces acting on him, he's got gravity here, or like at the center of mass, he's just got one force here acting at the center of mass. Okay, remember the center mass is 3/4. So what's happening is if you look at from the pivot, though, my r vector looks like this, and if I want to calculate the torque, it would be like Fg, and then you want the component of r that's perpendicular. So if this is theta, then we would say the net torque is FGR cosine theta, because this component of the r vector that's perpendicular to the gravitational forces, the adjacent side, cosine theta. So this is mgr cosine theta is the net torque. So basically what happens is you have the most torque at the beginning, and then when it's vertical, when the center of the mass reaches down here, then it's going to have no torque because the gravity is going to be down and it's going to be parallel to the r vector, right? So definitely we're going to have something where it like goes to zero torque and it starts at a torque, and we have to figure out what the shape of this graph is. And the tricky thing is that you have like something like this. So your alpha is this net torque, which is mgr cosine theta over IB. Now I want you to know that all of these parts are constant with they're all just constant with time. So I'm just going to make this as a constant times cosine theta. So let's look at what happens to the derivative of d theta dt, d alpha dt. That will give us shape. Hopefully we'll find that this is decreasing. Well, this is k. Derivative of cosine is negative sine theta. But then the derivative of, I have to multiply by the derivative of theta, which is d theta dt. And that's negative k sine theta times omega, because the rate of change of d theta dt is the angular speed. Okay, so this tells me that so omega is positive. We're saying this direction is positive, and then so this is negative, and sine is always positive because we're going from theta 0 to 0, like pi over 2. So this is always a positive quantity. So this whole thing is less than 0, which means it's decreasing. And that's what we knew. We knew it started there and went there. So that's nothing helpful. But we can look at the second derivative of this. And here I'm going to have to do product rule. So I'm going to pull out the negative k. And then I'm going to, derivative of sine is cosine theta times omega. Plus the derivative sine theta. Oh, oops. Derivative of sine theta is cosine theta times d theta dt. Plus sine theta times the derivative of omega, which is d omega dt. But that's negative k, it's cosine theta, d theta dt is omega. And then, oh wait, this is times omega also. So it's omega squared. Plus sine theta d omega dt, that's sine theta times alpha. Okay. Alpha is positive, sine theta is positive, omega squared is positive, cosine theta is positive. So this whole thing is less than 0. So that means it is concave down in shape. So concave down and decreasing means it's going to look like that. And then for omega, omega is supposed to be like, like the slopes of omega give you the alpha, right? So that means like this has to have a very big slope and then go to 0 slope. So it's gonna start 0, it's gonna end there, and it's gonna kind of go like this. Okay. Cool. While object B rotates from the horizontal position down through the angle theta shown above, is the magnitude of its angular acceleration increasing, decreasing, or not changing? Let's look at the magnitude. We say is decreasing. We said the derivative was less than 0. And the justification is d alpha dt is less than 0. I already kind of showed that before. I'm not going to write that again. Okay, object B rotates through the position above. Derive an expression for the angular speed of object B when its position shown above. Express your answer to MLB. Okay, so basically what's happening here is we're going to start at a position like this. And it's going to go down to this position. But if we think about it just from the center of mass point of view, the center of mass goes from here to here. Okay, so, and remember this distance here is 3/4 L. This distance here is 3/4 L, which means this distance is 1/4 L. This distance is 1/4 L. Okay? And we're going to do energy conservation. We're going to say this thing has potential energy at the center of mass. It's mg 3/4 L. Actually, let's make h equals 0 down this point, because we just want to talk about the change in the height. So from height from there to there, if you kind of reason it out, it's only 1/2 L from there to there. And then down here, it just has rotational energy, 1/2 IB omega squared. And we're just going to set them equal to each other. Now, this L over 2 really has to do because the center of mass only drops. It doesn't drop the full L. It only the center of mass drops L over 2. And so you can, the 1/2s cancel. And omega would be square root of mgl over IB. Okay. Number 3. Block of mass m is placed on top of an ideal spring of spring constant k. The block is pushed against the spring, compressing spring distance delta x. Block is released from elastic, leaves the spring in position shown in a figure, travels upward, enters a track with wow, that's kind of a mess. Exits horizontally at B, and then follows a projectile motion down. Express all answers in terms of m, k, delta x, r, and physical constants. The size of the block is much smaller than the radius of the curvature. Okay. On the dot, while represent, draw and label the forces that act on the block while still in contact with the track at point B. Each force must be represented with a distinct arrow starting on and pointing away from the dot. Okay, so point B, he's up here. So he's got gravity going down. And the track is above him. It's pushing downward. That's the normal force is pushing down. Okay. Justify your choice of vectors. Gravity always points down. Normal force is perpendicular to the track surface. Outward, which in this case is down. That's it. Derive an expression for the speed of the block at point B. Okay, so what we're going to do is we're going to compress it to this point, delta x, and then release it. So initially down, we're going to do conservation of energy. Yeah, because the normal force doesn't do any work, and is it frictionless? Negligible friction. Okay. So we're going to have, the energy here is going to be 1/2 k delta x squared, and then the energy here is going to have some, it has some potential energy. So it has spring potential energy here. And then here it's going to have kinetic energy and gravitational potential energy. So we just got to set those equal to each other. We're going to say that, well, I'm just going to do it up here so you can see it. So we're going to have 1/2 k delta x squared. And that's going to equal the gravitational potential energy gain, which is mg, and it gains a height of 3r, plus 1/2 mv squared. So if I multiply by 2, or if I bring this over and multiply by 2, so I have k delta x squared minus 6 mgr, because I multiplied by 2, is equal to mv squared. Divide by m, so v is equal to square root of k over m delta x squared, and then minus 6gr. So I'll write that down. V is equal to square root of k over m delta x squared minus 6gr. Derive an expression for the magnitude of the net force at point block at B. So net force is equal to, net force equals m times the centripetal acceleration, because it's moving in a circular path there, which is mv squared over r. So that's m over r times this whole thing squared, which is just gets rid of the square root. And if I distribute the m over r, it's going to be k over r delta x squared. And then the r cancels with that, so that's minus 6mg. Okay. Derive an expression for the minimum value of x-min required for the block to maintain track. So that means if it's just a maintain track, just to maintain, we would say the normal force is 0. which means that the net force has to equal mg. But we already know what the net force is. It has to equal this, k over r delta x min squared minus 6mg. And then you're just going to solve it. So I get 7mg. Adding the 6mg to the 1mg. 7mg is k over r delta x min squared. And then delta x min, see, multiplied by r divided by k and take the square root. So 7mgr over k. The procedure is repeated several times with the distance delta x is greater than delta min. Calculate the distance d that the block travels. Okay, so now if we look at the motion now, we have an initial velocity, and now we're subject to projectile motion, right? We found what this initial velocity is. It's equal to this thing here. And so now we just say it's going to fall a distance of 4r, and we want to figure out how long it's going to travel. So we need to find the time it takes to travel that 4r. So in the vertical direction, this is not a non-calculus based kinematics, but we're going to say delta y is 4r. The initial velocity in the y direction is 0. The final velocity, it doesn't matter. The acceleration is equal to g. And then t is what we want to find, because in the horizontal direction, we're going to use this time to calculate the distance it travels. It's just time times however long it's in the air times its speed. So here we would use this equation, delta y squared equal, not delta y squared. Delta y is the initial velocity in the y times time plus 1/2 at squared. So in this case, we'd have 4r. This part is 0, 1/2 gt squared. So that means t is equal to 8r over g, square rooted. And in the horizontal direction, we would just know that delta x is equal to v0 xt. So the distance we travel would be the initial velocity, which we found was the square root of k over m, delta x squared minus 6gr. And then times the time, which is the square root of 8r over g. So in this case, you can put everything in the square root and then just distribute. So 8rg times this is going to make it 8kr over mg delta x squared minus, the g's will cancel when you multiply that, so minus 48r squared. The graph below shows the best fit line drawn with students to the data as a function of delta x. Explain why there is no data for section 1 of the graph. If you're below x min, delta x min, then it didn't go high enough and it lost contact with the track, because it lost contact with the track. So the motion was not I would say the block didn't come out horizontally. With traveling horizontally at first. I'm just saying that it just basically didn't make it through the track. We'll just say, so the block didn't make it through the track. That's what I'll say. You want to be super cheeky. They could have recorded the data. They were just too lazy to. So you could just say, like, they just didn't feel like it. But this is physically why they didn't, because it kind of didn't make sense. What would happen is if you didn't do it far enough, you would have lost contact. That means at some point here it could have fallen down, or here. So it would have just fallen like this instead. And I don't know, like that's... Actually, it would have just fallen straight down. I don't know why I'm saying that. It would have... it would have lost contact. And so it would still have some horizontal velocity, I'd say. So it wouldn't go straight down necessarily. It kind of depends on where. If it ran out of energy, then it would. But like it could have lost contact right before and then just kind of fallen down. I don't know. Just sort of not really worth recording it because it's gonna have a weird. It's not gonna look correct, and it's really the motion didn't have the correct behavior. Explain the reason and the shape. Reason for the shape and minimum value. So d min. So if it maintains contact with the graph, with the track, then it travels a certain distance. It has some speed. So d is non-zero. And you could see that, and then we're going to use this equation a lot for the shape of the graph. Remember our derived equation, which is, I'm just going to copy it. Ooh. I don't know why I did that. Okay, so basically then, so that's fine, So that's going to be a non-zero value. Now, why does it look like a line? It's because, I mean, even though this is not a linear equation in delta x, you could say that, like, you know, the dependency, it's linear because the dependency on delta x is on the square root of delta x squared, which is delta x, which is a linear relationship. Now, in reality, if you were to graph this thing, it wouldn't quite be linear. It would really have to, like in the beginning part especially, it would probably be a little nonlinear. But as made delta, as delta x was much larger than this quantity sort of starts vanishing away. So it will approach like a linear shape. So you might expect it. It kind of depends on the relative weights of the constants, but you might expect the data to maybe it would have done something like this instead. But it would have approached a linear line at some point. As delta x increases, this thing definitely approaches a straight line through the origin. Okay, and that's it. So overall, I don't know if I thought this one was harder or not. This one, I thought the rotational question was a little trickier with the center of mass. Like finding like this part was the same as this part was almost identical to set 1. But I found the center of mass maybe to be a little more tricky. I don't know. It's hard to say. One is like the set 1 you had to do an integral to do the mass. This one you didn't have to do an integral for. You just kind of could do it from algebra. But I mean, I don't think the integral was like super hard. I guess you do a slight integral for A. I thought this problem was simpler than the fan one. I thought the fan one was a little tricky. You could have gotten tripped up with the fan changing direction. So I actually thought this one was a little bit easier. Overall, like in terms of more very, very straightforward problem. I thought maybe this, except for this part, I thought this part part D, I thought might have been a little harder compared to the problem set 1. This one, I'd say overall a little bit harder with the change in the shape and not understanding of the center of mass. Once you did that, then all of this stuff was kind of the same. This part, yeah, with the center of mass, this could have been a little tricky. If you weren't good with center of mass, or modeling it as a center of mass, then I think this would have been a little bit tough. This one was okay. Probably a lot of algebra, but I thought this one was pretty straightforward. I already forgot what the problem set. What was the problem set 1 look like for number 3? Sorry, I was just comparing to the problem set 1 a little bit. Yeah, I don't know. I kind of thought like it's comparable. I thought in terms of comparison of this one, I thought this one was probably a little bit more straightforward or more normal than the one where the spring and it jumps and it goes around and stuff like that. But I thought both of these ones were fairly similar. So overall, I would say maybe the problem set 2 is like, I would say like a little bit harder on some aspects. So yeah, but I hope you guys found that helpful and did well. Yeah, leave a comment if you have any thoughts.